Chapter 7, Tests of Significance and Measures of Association. In this chapter, you're going to learn how the empirical relationships between two variables is affected by random sampling error. This familiar theme of randomness applied. How to use an informal test in making inferences about relationships. Or how to use more formal statistical tests in making inferences about relationships. So we're going to look at both of these angles. How measures of association gauge the strength of an empirical relationship, and which measure of association to use in performing and interpreting political analysis. What's the difference between a test of significance and a measure of association? Well, a test of statistical significance, which in my opinion is probably the more important of these two elements. A test of statistical significance helps you decide whether an observed relationship to an independent-dependent variable, that is the relationship you're observing in a sample, really exists in the population, or whether it could have happened by chance when the sample was drawn. So the face-off here, the tension, is between what you're observing in your sample and what is going on in the population. Could what you have in your sample reflect what's going on in the population? A measure of association tells the researcher how well the independent variable works in explaining the dependent variable. So both these aspects of statistics come into play when you're trying to assess the significance but also the substantive strength of empirical relationships. Let's look first at statistical significance. And let's just take an example. These numbers are very close to the real numbers in the American National Election Study 2012. Suppose we have the American National Election Study and we calculate the mean Democratic rating among female and males in the sample. So we split the overall sample into two groups on the basis of the independent variable, gender, and we calculate a female mean rating of the Democratic Party at 54 degrees and a male mean of 49 degrees. So we have a 5-degree difference between males and females. Here's the question, and this question ought to be increasingly familiar given the topics that were covered in Chapter 6. Can we infer that in the population from which the sample was drawn, that females do, in fact, rate the Democratic Party higher than do males? So that's the core question that we're asking, not unlike the inferential questions that were asked in Chapter 6 about a single population mean. Now, here is the answer that we start with. We set this hypothesis up as a skeptical foil, the null hypothesis, which is symbolized by H sub 0. The null hypothesis always says, when we ask the inferential question about a relationship in a population, the null says this: no relationship exists in the population. Females and males give identical ratings to the Democratic Party, no gender difference. The null, the first line of attack for the null is to say, look, if you divide the entire unseen population up on the basis of gender and calculate a population mean for females in the Democratic Party rating and a population mean for males, and you subtract those two means, the true mean difference is 0. Well, our comeback would be that how did we obtain this, say, 5-degree difference we see in our sample? So here's the null's comeback. Any apparent relationship that we observe in a sample, like this 5-point difference that we found, was produced by random sampling error when the sample was drawn. So the 5-point gender difference is accounted for by random chance when the sample was drawn. You can see where we're heading with this. We're going to eventually calculate a mean difference between females and males, which we've already done, but then we're going to ask how much of that 5-point difference is random noise. Is there enough random noise in that difference to account for the whole 5-point difference? So our hypothesis, which is the alternative hypothesis, which is represented by H sub A, says that women do in fact give the Democratic Party higher ratings. This is called the alternative hypothesis and labeled H sub A. In order to have confidence that our hypothetical difference, we say we have a theory based on the gender gap, and we were expecting women to have higher ratings of the Democrats than males, and so we think the difference is produced by a systematic process. In order to have confidence in the alternative hypothesis. We must show that H0's version of events, the null hypothesis's version of events, it all happened by chance, is sufficiently implausible. That we accord the null hypothesis really an inordinate amount of territory. We have to be very sure the null hypothesis is incorrect in order to reject it. So we stack things in favor of the null hypothesis because there are two kinds of ways to get it wrong when we make an inference, type 1 and type 2 error. Type 1 error is bad error. Well, they're both bad errors, but this is worse error. Type 1 error occurs when the researcher infers that there is a relationship in the population when in fact the null hypothesis is correct. There is no relationship. So for example, suppose that based on a sample we infer that women do in fact give the Democratic Party higher ratings than men. If that is not true in the population, then we've committed type 1 error. And see, that's bad because I think that's worse because we're saying something's going on when in fact nothing's going on. Now, type 2 error is the sort of playing it safe error, the benefit of the doubt type of error. Type 2 error occurs when the researcher infers that there is no relationship in the population. Based on our sample, we say, well, we're just not sure enough that a relationship is going on in the population, when in fact there is a relationship. So we're not rejecting the null hypothesis, we're embracing the null hypothesis in type 2 error, when in fact in the population we're actually correct. This, I think, dramatizes the sort of asymmetry in inference that we have to get used to. Here's table 7-1 from the text, and this shows you the relationship. Of course, here's where we want to be. If HO is true, H0 is true in the population, and based on our sample, we don't reject the null hypothesis, that we've made the correct inference. That's good. If in the population H0 is false, that for example, in the population women do give Democratic Party higher ratings, and we reject the null hypothesis, then we've also made the correct inference. But the two types of error are dramatized here, represented here. Type 1 error, HO is true, there is nothing going on in the population, but we mistakenly reject the null hypothesis. That's type 1. Type 2 is up here. H0 is in fact false, but we just don't have enough confidence to say that, so we don't reject the null hypothesis. That's type 2 error. So we bias our inferential mistakes, if you will, toward the type 2 error end of the spectrum. In the last presentation, we introduced the null hypothesis and explained its crucial role in hypothesis testing and in tests of statistical significance. Let's pursue that question here and talk about exactly what standard we apply in testing the null hypothesis. We do know this. We always begin by assuming that the null hypothesis is true, and we set a high threshold for rejecting it because we wish to avoid type 1 error. So we're very conservative in this sense. Here is the inferential question. We ask, if in the unobserved population the null hypothesis is true, make that assumption, how often by chance will we obtain the relationship that we observe in the sample? You know, clearly, if the null hypothesis could explain our results, say 25% of the time by chance processes would produce our results, say 25% of the time, or 30% of the time, or even 15% of the time, we would probably say, well, you know, that's pretty frequently, so we won't reject the null hypothesis. What creates some confusion for students is that we also extend the null hypothesis's territory, if you will, all the way down to 6 times out of 100. So if we have a set of events that could be produced by chance 6 times out of 100, we still don't reject the null hypothesis because that is too frequently given the standard that we apply. So this is the 0.05 level of significance. If the answer to the question is more than 5 times out of 100, we do not reject the null hypothesis. If the answer is 5 times out of 100 or less, we reject the null hypothesis. So in statistical significance and hypothesis testing, we have to be, our level of confidence is, our definition of a rare or improbable event is an event that occurs 5 times out of 100 or less frequently. Our definition of a plausible or even probable event is any event that occurs 6 times out of 100 or more frequently. That's the cutoff. Now let's apply the standard in a couple of ways here. The first way you're familiar with. I mean, suppose we have a female mean, sample mean, we have a male sample mean. We would compute the confidence interval, the 95% CIs for each mean, and compare those CIs. I mean, obviously, if the two 95s do not overlap, we can reject the null hypothesis, and if they do overlap, however, we cannot reject the null hypothesis. Compare the 95% CI of 2 or more sample means. If the intervals overlap, then we cannot reject the null hypothesis. And the reasoning here is you get a sample mean that's a point estimate, but we know around that point estimate is an interval of confidence. It could be anywhere within that 95% CI. And if those two CIs overlap, then the two population mean could co-occur in the population. If they do not overlap, if there's distance between the 95% CIs, then we can reject the null hypothesis. And here's the example in the book. Again, we have over here the female mean 54.1 on the thermometer scale, the male mean 49.1. Instead of computing the difference, we're getting to that. That's the next approach. Simply compute the 95% confidence interval of the female mean, and just in the way we're familiar with, you would take the standard deviation and divide by the square root of n. That would give you the standard error of the female mean. You could multiply that times 2, add it to the sample mean, subtract that value from the sample mean, and we would come up with the 95% CI over here. So what we can say is that in the population from which the sample was drawn, the lowest plausible value for the female mean in the population is 53.1, and the highest plausible value is 55.1. Any claim within that range cannot be rejected. Every proposed population mean in that interval is plausible by this definition. Do the same for the male mean, 49.1. Figure out the standard error of the sample mean, multiply that by 2, and add it to 49.1 for 50.1, and subtract it 48.1. So the inferential question here is, does the lowest plausible female mean, 53.1, overlap the range of the possible male means? Well, the highest plausible male mean is 50.1, so these two plausible limits do not overlap. I'll just show you the math, or make this point reemphasize. The female mean is 54.1, standard error of 0.52. The lower confidence boundary, therefore, is 53.1. The higher confidence boundary is 55.1. Do the same for the males. The lowest 95 CI boundary is 48.1. The upper is 50.1. You know, so the most plausible, the highest plausible mean for men is 50.1. The lowest plausible mean for women is 53.1, and they do not overlap. This is what's called an error bar chart. I think there was an example of these in an earlier chapter. 95% CIs do not overlap, reject HO. Here's the female mean, there's the sample mean, and here's that bandwidth of confidence. It could be as low as the lower hinge here, but way down here is there's the male sample mean, and there's the highest plausible. Was it 50.1, I think? So all this white distance between these two confidence interval brackets, it represents a very low probability territory. And there's an extraordinarily low, we'll see how low in a minute, extraordinarily low probability that in the population the two means came from the same population. And so we would have confidence in saying, well, inside the population, yes, females do give the Democratic Party higher ratings than do males. We just looked at the confidence interval approach to testing for the difference between two sample means, and it's, again, like all CI approaches, it's durable. It won't lead you in the wrong direction, but it does lack precision. A more precise way to test for differences between two sample means is the probability value or the p-value approach. The idea here is to determine the exact probability of obtaining the observed sample difference, so we're going to focus on the difference now, under the assumption that the null hypothesis is correct. So again, the hypothesis testing logic is the same, but now we're going to focus on, instead of the two means and their CIs, we're going to focus on the difference between the means. The p-value approach is based on obtaining and evaluating the standard error of the difference between two sample means. And here's the table again, table 7-3 in the book. Here are the same numbers that we're familiar with. There's 54.1 for the female mean, 49.1 for the male mean. In this case, we're going to work with this difference of 5 units on this feeling thermometer scale. And so what we're after is the standard error of this difference, and just see how much of this 5, just how much error is there in that 5. How big could the difference be in the population? How small could the difference be in the population? Here's the process. We take the standard errors of each mean, and we square them over here. So the female mean, 0.52 is the standard error. We square it, 0.27. The male mean, the standard error is 0.53. We square that, we get 0.28. We add those two numbers, we sum them, get 0.55, and then we derive the square root of this 0.55 and arrive at the standard error of the mean difference, which is 0.74. Let's review those steps quickly, and then we'll see how we apply it. What was just done? 1, square each mean standard error. The square of the female mean standard error is equal to 0.27. The square of the male mean standard error is equal to 0.28. Sum these squared standard errors. In the example, 0.27 plus 0.28 is 0.55. Take the square root of the sum obtained in the earlier step, which is equal to 0.74. So the square root of 0.55 is equal to 0.74. That is the standard error of the difference. Now the so what question. We obtain a test statistic, and what we're going to do, we're going to convert the difference asserted by the null hypothesis here, which is always 0, because that's the null hypothesis' favorite number, and the difference we obtain in the sample, which is represented by the alternative hypothesis, which is 5 in the current example. That gives us a z statistic. Divide that difference by the standard error of the difference to standardize that difference. So many standard errors those two numbers are apart. The same test statistic, of course, can be computed for the t statistic. It's the same math. The distribution for t, as you know from the previous chapter, is different from z, but for large values of n, the two distributions are very similar. In both cases, the test statistic is 6.8. Now, what does this mean? This means that the null hypothesis asserted difference, or hypothesized difference of 0, and the observed difference of 5 are 6.8 standard errors apart. You know, imagine the standardized conversion of a normal distribution where z of 0 is on the mean, and then you go out 1 standard error in either direction, 2 standard errors, 3 standard errors. You know how thin the curve gets, how rarefied it gets when you get beyond, I don't know, 3 standard errors. The probability of those events out there are very rare. So imagine standing at 0 and looking down almost 7 standard errors into the frontier of the normal curve, and you get an idea just how remote the probability is that random processes produced a mean difference of 5. If in the population the mean difference between females and males is equal to 0, as asserted by the null hypothesis, how often by chance will we obtain a difference that's 6.8 standard errors from 0? And I had to ask Stata, a data analysis software, to return a probability. It's always a non-zero probability, but in this case the answer is about 400 times out of a billion. So if the null hypothesis is correct, and that chance processes produced this difference of 5 that we saw between the female and the male mean, that process would produce what we saw, an extremely fluky outcome 400 times out of a billion. Reject the null hypothesis.